Hello, and welcome to a little discussion about momentum and collisions. So, here's the deal. Nothing new under the sun here. Let me just skip to the first part where we start talking a little bit about impulse. There's this concept called impulse. We're going to use the capital J to mention this. Impulse is force applied over time. So force is in newtons, time is in seconds. The concept here is just newtons times seconds. So we're not talking about major new ideas. We're looking at the ideas that we've laid out as far as force and velocity and distance and work and energy and all those things. We're just looking at them through a slightly different lens to see if we can come up with some interesting ideas. So here's the idea. Impulse, it's a vector quantity. It has the same direction as the force, and we'll apply an impulse and see what it does. Turns out that impulse, force over time, what we're going to do is just take the average value of the force. So if you have a baseball bat striking a baseball, when the ball first comes into contact with the bat, it's a pretty light force, not very big force, and then the bat swings through and the ball is experiencing a really large force, and then as the ball and bat separate from each other, the force drops off again. So we have this big change in force, but if we just take the average force over the duration of that time, we have this impulse was imparted to the baseball. So another concept, momentum. Linear momentum of an object is a product of the object's mass times its velocity. Again, no new terms here. Mass is in kilograms, velocity is in meters per second. Momentum is a vector quantity, has the same direction as the velocity. Velocity is a vector quantity. Mass, remember, is a scalar quantity. And so linear momentum, vector quantity that we can describe things here. So let's put them together. Acceleration is the change in velocity over time. Force is going to be mass times the change in velocity over time. I'll multiply both sides by delta t. Force delta t equals mv final minus mv initial. Impulse equals the change in momentum. So this is the impulse momentum theorem. It says that when a net force acts on an object, the impulse of this force is equal to the change in the momentum of the object. So the impulse will change the momentum of our object in question. So rain comes down onto the roof of a car with a velocity of -15 meters per second, hits the roof of the car. The mass of the rain per second that strikes the roof of the car is 0.06 kilograms per second. Assuming that the rain comes to rest upon striking the car, find the average force exerted by the rain on the roof. Alright, so what we're doing, our force, which is acting for some amount of time, is going to change the momentum of the raindrop. We don't necessarily have the mass of each individual raindrop, but we do have that it's 0.06 kilograms per second. So we have a way to get to it here. So if we say change in time is in the denominator here, well, kilograms per second puts time in the denominator. Then we have mass times velocity with time. This is the impulse. And so we're able to then figure out, if we divide both sides by time, then we figure out that the average force is 0.9 newtons. If we have hail instead of rain, hail bounces off the roof of the car. It doesn't stop and stick. Well, in that case, would the force be smaller than, equal to, or greater than? So rain falls splat onto the roof of your car, hailstone bounces off. would that have a greater force? Well, does it experience a greater change in momentum? The change in momentum for the raindrop is just mv. So mv final is the final velocity at 6 to the roof of 0 minus mv initial. The initial was negative 15, so whatever the mass is times negative 15. So we wind up with a positive value for the change in momentum. The hailstone, the final velocity is positive. Even if it's not a perfectly elastic event, such that it's going up at the same velocity as it was coming down, it's a reasonably close approximation that mv final is some positive value minus mv initial. The initial was negative, so what we wind up with is a very big number, twice as big as the initial. So it would be greater. You'll have more damage done to your car by hail than you would by rain. The work energy theorem is related to conservation of energy. The impulse momentum theorem, then where does that come in? Well, if we apply the impulse momentum theorem to a mid-air collision between two objects, we would find that there are internal forces, that the objects, as they interact with each other, they each carry some x-axis velocity into the collision, some x-axis momentum, and they are both subject to y-axis acceleration due to gravity. So there's internal forces and external forces, and that's going to be important as we consider conservation of momentum. What we'll find out is that momentum is conserved, it's always conserved for our purposes, in so much as we consider all the internal forces that are involved. So we'll move on from this, because it's kind of a tedious point, and we'll talk about the principle of conservation of linear momentum. The total linear momentum of an isolated system, isolated so we're ignoring external forces, is constant. An isolated system is one for which the sum of the average external forces acting on the system is 0. So if you imagine two balls colliding on a billiard table that is friction-free, we're going to use momentum conservation principle in answering, is the total momentum of the two-ball system the same before and after the collision? Answer part A for system that contains only one of the two colliding balls. So if the two balls collide, then we'll find that momentum is conserved. And then what? For contains only one of the two colliding balls, well, we wouldn't see the same situation. So talk about total linear momentum of an isolated system is constant. Isolated system, blah blah blah. In the top picture, the net external force on the system is 0. In the bottom picture, the net external force of the system is not 0. Alright, so two ice skaters starting from rest push off against each other on the ice where friction is negligible. One is a 54 kilogram woman, the other is an 88 kilogram man. The woman moves away with a final speed, of 2.5 meters per second. Find the recoil velocity of the man. So here's a case. We're going to say that momentum is conserved. Momentum is the product of mass times velocity. So m1 times v1 initial plus m2 times v2 initial equals m1 times v1 final plus m2 times v2 final. You'll see that on any of our equation sheets. That's our classic way of describing the situation. Well, before the situation, m1 and m2 both have a velocity of 0. So the total momentum of the system before this event is 0. The final momentum of the system also has to be 0. The woman, 54 kilograms times a velocity of positive 2.5 meters per second, gives us a momentum, 54 times 2.5. She's carrying momentum of positive 135 kilograms times meters per second. He has to have that same momentum, equal and opposite. If he has a momentum of 135 kilograms times meters per second, and I guess we'll say it's negative, that's the product of his mass times velocity, then his velocity has to be negative 135 kilograms times meters per second divided by his mass of 88 kilograms equals 135 divided by 88, 1.53, negative 1.53 meters per second. I'm getting a negative number. That makes sense. He's traveling the negative x-axis, and he's not going as fast as she is. She has less mass, so she gets more velocity. He has more mass, he has less velocity. When we apply the principle of conservation of linear momentum, we decide which objects are to be included in the system. We're going to identify the internal and external forces, make sure that the system is isolated, and then set the final momentum of the system equal to its initial momentum, and remembering that momentum is a vector. Now, we're going to talk about elastic, inelastic, and then what we just talked about is an example of an explosive event. We'll get back to this in just a minute.